Hello everybody, welcome back. Today we're going to be covering subunit 1.7, which is on periodic trends. And I'm actually covering this one, 1.7, before 1.6 because it just makes more sense to me to teach it that way. So this is going to be a little bit of a lengthier unit, but I imagine a lot of it will be review from Chem 1. So have your periodic tables out because it's all about the periodic table today. Let's get started. All right, so there are lots of different trends on the periodic table. There's lots of different patterns, and every teacher teaches periodic trends a little bit differently, but the way that I teach it is by explaining to you a trend in one particular trend, and if you can understand that trend, then you understand all of the others, okay? And the way that I'm going to go about this is we're going to start off talking about what an electron is experiencing at any given time. Okay, so there's three things going on with an electron at least. Okay, so electrons, of course, are always moving, always have motion, so electrons possess kinetic energy, of course. I'm going to skip down to the third bullet point there. Electrons are also always experiencing repulsion from other electrons, and of course that's because like charges repel, so there's potential energy there. But the one in the middle, this is the big one. This is the one that if you can understand this, you can understand all of the periodic trends. Electrons experience a force of attraction to the nucleus, and that should make sense because the nucleus has positively charged protons. The electrons are negative, opposites attract. That attraction has a name. It's called the effective nuclear charge, and you can abbreviate it with its variable. It's a capital Z, EFF, okay, for effective. All right, so we're going to talk about the trend for effective nuclear charge, and again, if you can understand that, then you can understand everything. So let's talk about this trend for effective nuclear charge, and we're going to talk about it in the vertical direction first. All right, let's pick a family of elements like the alkali metals. As you go from lithium to sodium, potassium, rubidium, as I'm moving from top to bottom down a column, the effective nuclear charge, the strength of the attraction that those valence electrons feel towards the nucleus gets weaker and weaker and weaker. And let's talk about why that is. Okay, every time I move down a row, moving down a column, these atoms are gaining one more energy level. Okay, so the valence electrons are further and further away from the nucleus. The further away they are, let's think Coulomb's law. Okay, we talked about that last time. The greater that distance is, the weaker the force of attraction. Okay, so if we're looking at a column, let's again use the alkali metals, lithium versus francium at the bottom. Lithium is going to have, of those elements, lithium is going to have the strongest effective nuclear charge. Francium's valence electrons will experience the weakest effective nuclear charge. It's all to do with just increasing number of energy levels. All right, now let's talk left to right. All right, let's look at period number 2. So lithium to beryllium, boron, carbon, nitrogen. Okay, all of these elements have the same number of energy levels, and that's really important. Okay, so the valence electrons in that example are all on energy level number 2. However, as we move from left to right, those elements are steadily gaining one more proton, one more proton. one more proton in the nucleus. And let's remember, guys, think back to Coulomb's law. The strength of that positive charge, the magnitude of positive charge in the nucleus is increasing, okay? Thus, the strength of that attraction between the nucleus and the valence electrons is getting stronger. So from left to right, although these elements have the same number of energy levels, the elements are gaining increasing number of protons, thus the effective nuclear charge is getting stronger. Okay, now let me just say one thing. When you come back to the vertical direction, as you go from lithium to sodium to potassium, you might say, well, wait a minute, Miss G, when you're going from top to bottom, you're gaining additional protons in the nucleus as well, and you're right. However, the distance, it's like it's a bigger deal, okay? Yes, we're gaining additional protons in the nucleus as we move top to bottom, but those valence electrons are moving further and further away from the nucleus, and that is a bigger deal, okay? Distance from the nucleus is always a greater factor than the number of protons in the nucleus. Okay, so I want you guys to think about this. I want you to look at your whole periodic table. Think about the trend up and down, the trend left to right. What element on the periodic table must have the weakest effective nuclear charge? That should be francium, the lower left. So let's flip that around. What element must have the strongest? That would be helium. Okay, so that's the trend, and if you can understand that, you can understand all the other trends. Okay, so this slide just solidifies what we just talked about. Okay, when you're talking about up and down, it's the increasing number of filled energy levels between the nucleus and the valence electrons. When we're talking left to right, okay, we're on the same energy level, but electrons are more strongly attracted because of additional protons. Okay, so when it comes to periodic trends, for whatever reason, the AP exam tends to focus on ionization energy as the one that they have decided is like the most important. Okay, so let's remember what the term ionization energy means. It's the amount of energy required to remove an electron. Okay, so let's talk about it. Okay, and I realize that it has this word first here in front of the term ionization energy. I'll get to that later. Okay, so what's the trend in ionization energy? Okay, well, let's remember, guys, what was the trend in the effective nuclear charge up and down? As you move from top to bottom, effective nuclear charge, the strength of the attraction between nucleus and electrons weakens. So what does that mean? As I move down, is it easier to take a valence electron or more difficult? It's going to be easier. So ionization energy will decrease as you move down a group. And the reason is the same as all the others, all the other trends, because the effective nuclear charge is weakening because of additional filled energy levels. When we look left to right, remember, the effective nuclear charge is getting stronger. Same number of energy levels, but increasing number of protons. So as I move left to right, those electrons are being held with a greater and greater attraction. It's going to be more and more difficult to take electrons away. So ionization energy increases from left to right. Okay, and we just talked about why that is. So you guys tell me, think about it. what element must have the lowest ionization energy value, the element that it is the easiest to take an electron away? It's going to be francium. The one that is the most difficult, the greatest ionization energy, it's going to be helium. Okay, let's get to why that word first was there. Okay, first ionization energy means the energy required to remove one electron. A second ionization energy means you have already taken one electron away, and now a second one is going to be removed. Okay, and you can have third ionization energy, fourth ionization, etc., etc., etc. Okay, and there is a trend here. Okay, and I don't get to say this very often in AP Chem, but this is true no matter what, no exceptions. No matter what element we're talking about, this relationship right here, whatever an element's first ionization energy is, the energy to take another electron away is always going to be greater. And if I wanted to take a third electron away, that's going to require even more. Okay? And the reason for that is because the effective nuclear charge is increasing. Every time you take an electron away, the attraction that the remaining electrons feel is going to be stronger and stronger and stronger. It's almost like a tug of war. Okay? You've got protons on one side of the rope, you've got electrons on the other side of the rope, and I keep removing team members from the electron team. Well, that means the remaining electron members of this team are going to feel a stronger pull from the nucleus. And I want to show you some numbers here, okay? This is for the element magnesium, all right? And I want you to notice that the numbers are increasing here. Here is its first ionization energy. Its second is more. It takes more energy to remove that second electron. It takes even more to remove that third. Okay? A fancy way that you could explain this, let's say this was in a free response situation. Okay? And maybe the question said, please explain why the ionization energies are steadily increasing. Okay? You could simply talk about the proton to electron ratio. It's increasing in favor of the proton, so the effective nuclear charge is getting stronger. Now, I want you to notice that from ionization, the second to the third, yes, it increases, but it increases a lot. There is a big jump between ionization energy 2 and 3. And I want you to pause the video for just a second. Look at where magnesium is located on the periodic table. And I want you to just think for a second, why might there be such a big jump? So just pause and think for a moment. Okay, so here's magnesium, right? Okay, right here. Magnesium has 2 valence electrons, right? Okay. Removing the first, okay, the first valence electron, okay. Removing the second, okay. Removing a third, ladies and gentlemen, removing that third electron from magnesium is not removing a valence electron. It's removing a core electron. And not just any core electron. It's a core electron from, where am I? From a filled energy level. And that's a big deal. That takes a lot of energy. So why is there that big jump? Okay, It takes much more energy to remove a core electron, and not just any core electron, but one from a filled energy level, than a valence electron. So let's look at another one. Okay, I want you to look at where aluminum is on the periodic table. Look at these numbers, and let's say this is a free response question. Okay, explain this trend. Okay, why? Think of it like a two-part question. Number one, why are the numbers steadily increasing? Let's say that's part A. And part B, why is there such a large jump between the third and fourth ionization? I want you to think about how you would write that out as a free response question. So pause the video, think about it. All right, so why are the numbers steadily increasing? Okay, every time an electron is removed, the proton to electron ratio is increasing, and thus the effective nuclear charge is increasing. Greater amounts of energy are required to remove successive electrons. Okay, that's like part A of the question. Part B, why is there such a big jump between the third and fourth ionization energy? And you could say something like, removal of the fourth electron is removing a core electron from a filled energy level, which requires much more energy than removal of a valence electron. Something like that. All right. Okay, now, just to make sure that we've got this, let's just kind of recap a little bit. Okay, in fact, let me take that off the screen. From left to right, ionization energy increases, and that's because the effective nuclear charge is getting stronger, is also increasing. However, and this is like the essence of AP Chem, here's a big rule. Oh wait, there's a whole bunch of exceptions. And here's one of them. Explain why there is a slight decrease in ionization energy going from elements in group 2 to 13. And I have some actual numbers for you. I'm not making these numbers up. Okay. We're going to look at magnesium versus aluminum. Okay, and magnesium's first ionization energy is 735 kilojoules per mole, and aluminum's first ionization energy is 580. Okay, now wait just a second. I just said ionization increases from left to right, but clearly there's something weird going on here. Okay, and I want you to think about these valence electrons, okay, for these elements. Magnesium has 2 valence electrons, aluminum has 3. Okay, so I'm going to circle the electron that we are trying to remove here. Okay, pictures speak 1,000 words. Okay, what these numbers are saying to me is that it's more difficult to take that electron than it is to take aluminum's electron. It takes more energy. And why is that? Well, ladies and gentlemen, and I hate to give elements personalities because they don't have feelings. They don't. Okay, but atoms are kind of OCD, all right? They like order, they like symmetry, they like things to be full and not just partially filled, things like that. Okay, taking an electron away from magnesium is taking an electron away from a filled sublevel. Okay, this, before I took that electron away, that was a filled 3s sublevel. Whereas taking this guy is taking an electron away from a partially filled 3p sublevel. Okay, so let me break this down for you. Here's the company answer. This is what you would write on the test. Okay. More energy is required to remove an electron from a filled 3s sublevel than from a partially filled 3p sublevel. Okay? It's almost like magnesium had this nice full sublevel. It doesn't want you to disrupt that. Okay, but again, elements don't have feelings. Please don't ever say want on the test. Magnesium doesn't want something. All right, more energy is required to take an electron from a filled 3s sublevel than from a partially filled 3p. All right. Unfortunately, there's another exception to the rule. Going from elements in group 15 to 16. Okay, so, oops, let me change color here. I'm just going to use nitrogen and oxygen as an example, and this time I am just going to make up some numbers. Let's say nitrogen has a first ionization value of 840 kilojoules per mole. And let's say that oxygen has a value of 760. Okay, again, ionization energy should increase from left to right. But there is an exception in this position from 15 to 16. And again, pictures speak 1,000 words. I'm going to draw out nitrogen's 5 valence electrons and oxygen, let me write it down here. Oxygen has 6 valence electrons. Okay, and I'm going to circle the one that we're trying to remove. So what are we taking away from nitrogen? We're trying to take an electron away from a half-filled 2p sublevel, whereas in oxygen, again, we're just taking an electron from a partially filled sublevel. Okay? It's almost the exact same wording as in that first exception at the top of the slide with just one word different. Are you ready? Here we go. It takes more energy to remove an electron from a half-filled 2p sublevel than from a partially filled 2p sublevel. Okay, again, elements are sort of OCD. Nitrogen didn't have a filled p sublevel, but it had a half filled, and that's pretty good. And it doesn't want to have that disrupted. So let me say again. It takes more energy to remove an electron from a half-filled 2p sublevel than from a partially filled 2p sublevel. So there are some exceptions. So if you're asked some ionization energy questions where elements are around this group 2 to 13 border, like beryllium to boron or magnesium to aluminum, or if they're on that 15 to 16 border, just slow your thinking down and be real careful. Okay. All right. So let's look at this question. Okay, we're given 3 different elements. All right, and let's just go ahead and label them. Let's just identify what those elements are. 1s2, 2s2, so that's neon, sodium, and magnesium. Okay, and the first question says, which atom has the largest first ionization energy? I hope you said neon. Okay, not only does neon have 1 less energy level than the other 2, okay, meaning its valence electrons are one energy level closer to the nucleus. They're experiencing a stronger effective nuclear charge, but neon also has a filled energy level. Taking an electron away from a filled energy level is a big deal. Which one has the largest second ionization energy? Let me ask that to you in another way. Which of these elements would we see a large jump between the first ionization and the second? I hope you said sodium, okay? Because sodium has one valence electron. Okay, we're going to take it away. To take a second electron away from sodium is that whole core versus valence. You're taking a core electron, and not just any core electron, but a core electron from a filled energy level. That's a big deal. That takes a lot of energy. Okay, now, this is not a mystery because we have already learned the why behind this trend in atomic radius. Okay, when you move from top to bottom, what happens? Atoms gain increasing number of energy levels. Well, and that must mean the atom is getting bigger. Okay, what happens when we move from left to right? Same number of energy level, but increasing number of protons means that the effective nuclear charge is getting stronger, so the radius decreases. Okay, some of your teachers from Chem 1 might have said, remember the snowman, and then you knock the snowman over. Okay, and he's all sad face. Okay, so that's a way to remember the trend, that it gets larger as you move down, it gets smaller as you move to the right, but please do not say on an AP exam or a test or anything, oh, it's because of the snowman. No, you can't say that. Talk about effective nuclear charge and the why behind that. Okay, so atomic radius, let's talk ionic radius. Okay, guess what? It's the same trend, okay, for the same reason. All right, but let's talk about a couple of things here. All right, I want to compare with you two particles, a calcium atom versus a calcium ion. Okay, and let's decide which one is, let's go with which one is smaller. All right, well, think about it. A calcium atom has 4 energy levels. What happens to a calcium ion? It has lost 2 electrons, and it lost its 2 valence electrons. So if you look at your periodic table, if you take those 2 valence electrons away, it now has only 18 electrons, and that means it only has 3 energy levels. So which particle is smaller? That would be this one. Okay, let's talk about anions. How about I ask you to compare these two? This one's a little trickier. Okay. Fluorine has 2 energy levels. Okay, fine. Fluorine with a -1 charge, what happened? It gained 1 electron, now it has 10 electrons, and that also has 2 energy levels. Okay, well, which one is going to be the larger one? Okay, well, think about it, guys. You add an extra electron in there. Remember, there's electron-electron repulsion. Okay, electrons don't like to be near each other. Like charges repel. So the size of the particle is going to expand. So this guy's going to be bigger because of electron-electron repulsion. So sometimes you can answer the question of which particle is larger based on how many energy levels does it have, but sometimes you have to look at other factors. Okay. All right, now I'm going to pull up a picture here to illustrate these next two bullet points. Okay, I want you to look at this. These are the ions going across period 2, okay? And what I want you to notice is that these particles on these first 4, they're getting smaller. Okay, fine. These 3 are getting smaller, but there's this huge jump between the carbon ion and the nitrogen ion. And let's think about why that is. Okay, let's talk energy levels. Look at your periodic table. Lithium that loses its 1 valence electron, how many energy levels does it have? Just 1. Beryllium that loses its 2 valence electrons, how many energy levels does it now have? Guess what? 1, 1, 1. Those first 4 ions all have just 1 energy level. Look at nitrogen, however. Nitrogen, look where it's located, is going to gain 3 electrons. So it's not going to have 7 electrons anymore. Now it's going to have 10. That's 2 energy levels. And guess what? So do these. So that's why you see that big jump. Even though these ions are in the same period, it's because they have different number of energy levels. Okay? But let's go one step further though. Why are, from nitrogen to oxygen to fluorine, why are those ions decreasing in size? Guess what, guys? It's the same reason we've been talking about. Yes, they all 3 have the same number of energy levels. They all have 2, nitrogen, oxygen, and fluorine, but they have increasing number of protons. Effective nuclear charge is increasing. That's the same thing we keep hearing again and again and again. Okay. All right. Now, this is a vocabulary word I want you to know. The prefix iso means same. Isoelectronic, same number of electrons. Okay? All 7 of those particles up there, all of them have the same electron configuration. 1s2, 2s2, 2p6. They all have 10 electrons. Those are called isoelectric particles, or iso, sometimes you'll see it just isoelectronic or isoelectric particles. Okay. However, do you think they have the same size? I assure you they do not. Okay. And look at them. Okay. All of them have 10 electrons. That means all of them have 2 energy levels. So why is the aluminum ion the smallest? Because, ladies and gentlemen, it has the greatest number of protons. It has the greatest proton to electron ratio. It has the strongest effective nuclear charge. Thus, it is the smallest. Those outer electrons are experiencing the strongest attraction to the nucleus. Think back to Coulomb's law. Okay? That nucleus of the aluminum atom has the greatest magnitude of charge. Thus, it's going to have the strongest attraction, smallest radius. So what I want you guys to do is put these isoelectric particles in order from largest to smallest. All right, let's see how you did. Okay, so that's the order, right? They all have the same number of electrons. They are isoelectric, same number of energy levels. However, P, the phosphorus ion, is the largest. Why? Because it has the fewest number of protons. Thus, it has the weakest effective nuclear charge. Calcium has the most number of protons in this list. Thus, it has the strongest effective nuclear charge. All right, we are just about done here, almost. Okay, let's talk electronegativity. This is our third trend on the periodic table. Let me refresh your memory on what that term means. The ability of an atom in a molecule to attract shared electrons to itself. Now, later on in the year, we're going to talk about bonding, in particular covalent bonding here, where two atoms share electrons between them. But for now, what we're going to just make sure you know is which elements will attract those shared electrons more than others, okay? And there are some electronegativity values which you don't need to know. They're called Pauling values, okay? And they're just how electronegative certain elements are or are not, okay? And guys, guess what? It's the same trend, okay? When you move from left to right, what happens to the effective nuclear charge? It increases. That means the nucleus is attracting its own electrons more and more strongly to itself. Well, guess what? If the nucleus attracts its own electrons more strongly, don't you think it could also attract the electrons from somewhere else as well? And yes, it can. Same trend moving from top to bottom. Effective nuclear charge decreases as you move down a group. So, elements become less and less electronegative as you move from top to bottom. Okay? Now, we don't discuss noble gases when it comes to electronegativity because noble gases typically don't bond with other elements, and electronegativity is all about electrons between two atoms, and since noble gases don't really bond, we don't talk about them. So I want you to look at your periodic table, put your hand over to cover up the noble gases. Excluding the noble gases, think about the trend. What is the most electronegative element? It's fluorine, okay? Excluding the noble gases, fluorine has the strongest effective nuclear charge, thus it's going to attract shared electrons the most. Again, francium will be the least electronegative element, okay? And we're going to talk more about bonding later on in the year and what happens when you have elements that are very different in their electronegativity. This is our last periodic trend, and it's very brief. I saved it for last because it's the one that is covered the least. It's called Electron Affinity. Okay, and it's kind of the opposite of ionization energy. Ionization energy is the energy associated when an electron is removed. Well, this is the energy associated with the addition. An electron is added. Okay, and here's the deal. Okay, the more negative the energy, the more that is released, the more exothermic, the more negative an electron affinity value is. It's like that element really, I hate to say wants, but the more that element wants to gain an electron. Okay, so I want you to look at your periodic table. Can you think of a family of elements that would really, I'm putting this in air quotes, that would really like to simply gain one electron? It's your halogens. Because think about it, why would your halogens really, quote, want to gain an electron? Because that would give them then a filled energy level. So guess what? your halogens have a have a great electron affinity. Okay, the word affinity means you alike for something, right? The halogens, and in general, guys, your non-metals, okay, tend to have very negative electron affinities. Okay, those are elements that would very much, quote, like to gain electrons, whereas your metals, on the other end, would very much not like to gain an electron. So metals tend to have very endothermic, positive electron affinities, meaning they don't want to gain an electron. Okay, I wouldn't worry too much about electron affinity. It does not show up on the AP exam too often. Again, ionization energy and atomic radius, those are the big ones. Okay. So I have thrown a lot at you today. I know this was a longer lesson. A lot of it should have been review from Chem 1, but it always is good to just hear it again. So thank you for sticking with me through this, and I hope you all learned something today, and I look forward to seeing you next time.